Good morning, everyone. I'm Anders Hejlsberg, a technical fellow at Microsoft, and I'm excited to be here at our virtual TSConf. Thanks to all of the Nicks for the intro, and really a big thanks to SitePen for putting this on again. This is the third TSConf, but I primarily want to thank all of you for all of the support that you've shown by using TypeScript and continuing to grow the community. It's really the thing that keeps our team motivated, keeps us going, is all of that enthusiasm out there. Obviously, this year's event is a little bit different from the previous years. Everything is different this year, really. I, in particular, will sort of miss the personal interactions that we've been able to have at the other conferences, but most of all, I miss the swag. But I still have the swag from last year, and I'm going to give this talk wearing my TypeScript socks. So I'm all properly equipped here. This talk is sort of a year in review of what's been going on with TypeScript. I'm going to talk a little bit about how we operate and why we do what we do, and then talk about what's happened in the last year in the community and in the product. And then, of course, we're going to take a look at what's coming up next in the product, and then finally I'll wrap up. You may have seen this slide before. I like it because I think it really perfectly in one picture summarizes why we exist. You know, JavaScript is a language that has issues, pitfalls, and whatever, but there are some good parts in JavaScript, and really we see our job to be helping you avoid the bad parts and amplifying the good parts. And the primary way we do that is by adding a static type system to JavaScript. And then using that static type system, we build excellent tooling on top. And really the static types are this deep enabler for really everything that powers modern IDEs today, you know, like things like online error messages, like red squigglies, errors, compile time type checking, code navigation, statement completion, go to definition, et cetera, et cetera. Now, TypeScript turned 8 last week, in fact. It's amazing that it's been this long. Here's a picture from the day we officially unveiled TypeScript at TSConf in Aarhus, Denmark in 2012. This is myself in the middle, and then we have Steve Luco on the right-hand side of the picture, and Luke Hoban on the left-hand side, wearing traditional head garb of my youth. We've learned a lot in the 8 years that have since transpired. Our community has grown tremendously. We've learned a lot about how to do open source and how to do open development. And really, we've distilled it down to these sort of 6 operating principles that govern how we run the TypeScript project. As I said, we are open source and open development. We moved the project to GitHub about 6 years ago now, and the entire team operates on GitHub day to day. That is really our workflow. And we're deeply committed to staying open source for forever. We see it as our job to closely track the ECMAScript standard, but not to actually make new features in the ECMAScript language or in the JavaScript part of the language. In fact, we participate in the ECMAScript standard. We have represented 2 of our team members are representatives in ECMAScript, and we've championed several proposals and are very much involved. But really, where we innovate is in the type system, and that's sort of where we see the place where we add value, and we have indeed continued to innovate, and we will continue to do that. And really, the job of the type system here is as I said, to to power best of breed tooling. And that's why we do the type system. We also really continuously strive to lower the barrier to entry. Of course, TypeScript is a superset of JavaScript. And that means a lot of people come from JavaScript, and some people want to just stay in JavaScript and don't necessarily feel like it's worthwhile to add manifest type annotations and have a compile step and so forth. And so we've invested a lot in using all of our TypeScript infrastructure just for plain JavaScript. So, for example, we now fully support JSDoc annotations, and we can slurp up type information from JSDoc. And we use the TypeScript compiler as the language service when you're coding in JavaScript in VS Code, for example. And then finally, community. It's we are deeply committed to staying engaged with the community, and the fact that we're on GitHub means that we are right there. There's zero distance between us and you, and we're constantly monitoring the issue tracker and answering questions and so forth. The TypeScript's type system is interesting in that it has a bunch of features that I've never really seen combined in any other type system. Some type systems may have some of these, but this notion that we are erasable and a gradual type system is fairly new in type systems research. We're structural. Where most type systems tend to be nominal. We are heavily generic. We do heavy-duty inference. We're also very expressive, and in fact, we have a whole bunch of type constructor or type concepts that really only pertain to JavaScript, such as index access types, and then you'll see like tuples and some of the newer features that we're investing in. And then we support both object-oriented and functional programming styles. Looking a bit at what's been going on is since in the last year, well, here's the last year and a half, but since the last TSConf, also which was a year ago, about 18 months ago, we decided to go on a fixed 3 months release cadence. We now release product every February, May, August, and November, and we have been on that cadence now for the last 18 months. And as you can see here, TypeScript 4.0 is our latest release, and TypeScript 4.1 is indeed slated to release in November. And the growth in our usage has been phenomenal. We have literally, I think now for 8 years going, seen a doubling every year of the number of downloads that go on NPM, and indeed we managed to double yet again in the past year. Of course, the law of large numbers is going to make this impossible eventually. But it is truly astounding that we now average about almost 60 million downloads per month on NPM. Some other interesting metrics. There's this big state of JavaScript survey that's done every year. This is the 4th year. This survey has more than 20,000 participants. And you can sort of see our growth here. The red is the number of people who have used TypeScript and will use it again. And we have grown, to now be at almost 60% of what I would classify probably as professional JavaScript developers, since they're the ones responding to this survey. But that is truly astounding that we have penetrated more than half of all professional JavaScript users. And an additional 22% say that they've heard of it and would like to use it. So if you sum those up, we're close to 80%. Here's another metric that is actually quite recent. This is the second quarter of this year, and this is looking at how many pull requests were submitted on GitHub, grouped by language. And you can see TypeScript is now at number 6 and climbing, which is quite amazing. And of course, if you sum up TypeScript and JavaScript together, since they really are just sort of close cousins, that's almost that's more than 25% of all pull requests on GitHub. This survey is, or this slide here is from the Stack Overflow annual developer survey, which is surveys, I think, more than 60,000 developers. And I particularly like this category here. What is the most loved programming language? Where we this year managed to eke out second place, which just passed Python, which of course makes me very happy. I'm not going to talk about which language is the most dreaded. I'm going to leave that to you to guess. Here's our team. It's not a very big team, less than 20 people. This picture is actually from last year, and of course, we wanted to take a picture of our team this year, but this is what our workflow looks like now, obviously. But I will say it is remarkable how this team has just not missed a beat in spite of all that has happened this year. We were already sort of half remote in that half of our team members are distributed all over the world, but at this point all of us are remote. Yet all of our processes have just continued without skipping a beat, and I can only attribute that to this fantastic team of people that I get to work with every day. So let's talk a bit about what's happened in the TypeScript community in the past year. You probably know that last year we did a bunch of work to support TypeScript in Babel. In fact, our team did a whole bunch of work to submit pull requests that allows Babel to transpile TypeScript. And that it's been great to see how that work has continued this year, and largely has been taken over by the Babel community itself. And I think the latest release of Babel 7.11 has TypeScript 4.0 support, and there's work ongoing to add TypeScript 4.1 support already. ESLint is another one of those tools that where we a year ago we retired, or the community retired TSLint and put a big amount of effort into converging on a single linter, ESLint, that the ECMAScript community already uses, and that work again has been ongoing this year. And the TypeScript ESLint project that exists to translate the TypeScript AST into ES3, which ESLint uses, is just running real smooth. And one of the sort of fantastic benefits of this combination is that it's now possible to write linter rules that use semantic information from TypeScript, where linters typically really could only look at syntactic and grammatical constructs. Now it's possible to actually consult the TypeScript type checker in your linting rules, even for JavaScript. Another newcomer here in the community is Dino. They ship Dino is an evolution of Node. It's built by built by Ryan Dahl, or started by Ryan Dahl, who was the original author of Node.js. They shipped their version 1.0 in May of this year, and it's a very interesting project, one that we're very enthusiastic about. It supports TypeScript built in. It's a single executable download. It uses URLs to find modules and whatever, all sorts of interesting stuff. It's probably still at a researchy stage, but it's a good project. There are lots of frameworks out there in the ECMAScript community, and we really see ourselves as being completely framework neutral. One thing that's amazing is that all of them now, all of these players here and many more, all support TypeScript. Angular is written in TypeScript. React is not, but React CLI fully supports TypeScript. Vue 3.0 supports and is written in TypeScript. Large parts of Ember are written in TypeScript. Large parts of Svelte also. And it's nice to see all of that adoption. And we're deeply committed to working with each of the owners and maintainers of these frameworks to make sure that we have the best possible experience in the TypeScript toolset. A lot happened in our playground this year, all pioneered by Orta, one of our team members. In fact, there's so much there that there's a whole separate talk about what happened in the playground that you can watch later this afternoon. There's definitely a bunch of cool stuff. Definitely Typed is such an integral part of our community. It is consistently one of the 10 most active repos on GitHub. Up today, there's been about 12,000 individual committers on Definitely Typed, which is just amazing. And since about 3 or 4 years ago, the community urged us to get involved in helping manage all of the information that's on Definitely Typed. And we've done a bunch of work. We don't actually write any of the type definitions that are up there, but we do build a lot of the tooling that powers Definitely Typed. We build a lot of the tooling that packages up type definitions and deploys them under the @types namespace on npm. And you know, there's about 250 pull requests per week going on Definitely Typed. Every week we have a rotation where if a team member is on Definitely Typed duty a week at a time, and that has been a big drain. And so we've invested heavily in building tooling that also eases that workflow, and new this year was sort of the ability to have self-merging, we call them self-merging pull requests. It really boils down to a bunch of bots that check that a PR has all the appropriate tests, passes all of the continuous integration, and that the owner has approved it, and then ultimately allows the author to just merge the PR themselves. And that has cut down a bunch of the workload, and now about 20 PRs daily are merged just by the community itself, which is great to see. Discord is another place where that has grown tremendously for TypeScript in the last year. There's about in the TypeScript Discord community is about 2,100 concurrent users at any given time. It's a great place for newcomers to land and ask questions. And of course, there's also Stack Overflow. So, and last but not least, I want to give big thanks to all of the community contributions. As you can see, it's hard to fit it all on one slide here, but lots and lots of product features now are being built by the community. And it's wonderful to see that engagement and keep it coming. We're very committed to this whole process of the community building their favorite features. So that takes me to what's new, and I'm going to first talk about what has happened in the last year, and then after that we'll take a look at what is coming. And I've sort of divvied it into a few different buckets. First we'll talk about new ECMAScript features, then new type system features, then new tooling features, and then also look a little bit about what's happened to our website and documentation. So as I said, we closely track ECMAScript, And generally speaking, whenever proposals reach stage 3, we endeavor to implement them in the TypeScript compiler. And last TSConf, you saw me demo optional chaining and nullish coalescing. They are now in the language. New this year is private fields, which was built by Bloomberg. Thank you very much. Also, export namespace from and logical assignment operators. We'll take a look at a few of these. Let me start by looking at private fields. Here we go. So let's try to zoom this guy here. Oops, there. So private fields are basically the ability to sort of prefix your property names with pound, and that gives you a new namespace where all property names are completely private within the declaration of a class. So pound name here is only visible inside the class declaration and cannot be accessed outside. This is unlike the private modifier in TypeScript, which really is just a compile time feature. The private modifier gets completely erased, and at runtime, it's just a regular property. And you may go, well, that's fantastic. Why would I ever then use the private modifier? When we compile this code, if you're running on the ESNext, which my config options are set to right here, then the compile code looks very nice. I mean, we just erased the type annotations, right? But let's say that we switch to ES 2015 and we compile down level, for example, and let's try to build here, and then let's look at the code that comes out of that now. There we go. And you'll see that private fields are pretty heavy-duty transformation that happens to the code. You still see the class in here, but now because guaranteed privacy really isn't possible with regular properties, instead we emit code that creates a weak map for every property name and then stores the property values into that weak map. And obviously there's some overhead associated with storing your state that way. Depending on your program, it may range from not measurable to as much as 10x overhead. And so if you plan to use private fields and you plan to use them down level, I would recommend that you measure and just make sure that your performance is not too adversely affected. But of course, ultimately, this will end up in ECMAScript itself. Hopefully, the proposal is still at stage 3, but it is implemented by V8 natively currently. So that's private fields. Another feature that is new from ECMAScript is logical assignment operators, and let's try to look at, whoops, no, that was not the right. Ops here. So you're all probably familiar with the Boolean logical operators, or, and the new nullish coalescing operator that allows you to substitute a value when something is null or undefined. And of course, in JavaScript, all operators have had a compound form where like you can write plus equals, minus equals, and so forth. But strangely, the logical operators did not have the assignment form. But that is new and slated to be in the next release of ECMAScript. And we now implement that in TypeScript. And we can look at the compiled code when you use this operator here. You'll see that the thing that's interesting about it is that the assignment does not take place unless the test, in case of the or the assignment only takes place if A is falsy or truthy, respectively. or if A is null. And that actually matters, and that is really sort of the difference between writing A or equals something versus A equals A or something, is that the assignment only takes place when the thing is falsy or truthy. And if you have a property accessor, for example, that means that your property accessor won't even be called in that case. So that's this feature. I'm going to move on to, because we've got lots to show here, I'm going to move on to some of the new type system features. I showed some of the newcomers already at the last TSConf, such as assertions, recursive type references, and uncalled function checks. New this year is support for type-only imports and exports, which makes it easier to control when a module is referenced in the transpiled JavaScript. And with type-only imports, you can ensure that the only thing you import from another module is types, and therefore that in the runtime version of your JavaScript, the module will actually not be required. We have some work to reduce intersections by discriminants. This is sort of more in the area of correctness of type checking for discriminated union types. And then a particularly interesting feature is variadic tuple types. And variadic tuple types is sort of a continuation on a saga, long-running saga to finally fix this issue called variadic kinds, which goes back 5 years and has been extremely popular, as you can see, upvoted to almost 800 upvotes. And one meta comment here is we do pay close attention to these upvotes, and this is why we devote time to it, because clearly the community is showing us that this is a feature that everyone wants. And so about 2 years ago in TypeScript 3.0, we introduced variadic. We introduced certain additional features in tuple types, like optional optional elements and rest elements, and we added support for variadic functions that could capture parameter list in tuples, but all you could do with that was capture entire parameter lists, and then sort of spread them back into another function call. But we did not add the ability to slice and dice tuples themselves, and that is really what variadic tuple types are about. And let's try to take a look at that in action. In a nutshell, this feature is about allowing variadic holds in your tuple type declaration. So previously we would allow you to put a T here, for example, and say you could say this element's type is T, but we would still know that there is an element here, and we would still know the exact size of the tuple, so to speak. So all tuples always had a static layout. It's just that you could vary the types of the elements. But with variadics, you can actually create holds that can be filled by other tuples, and they are variable length in nature. So you could spread in nothing or any number of other elements here, and that happens through instantiation, of course. So if we, for example, instantiate foo with a tuple of a single element Boolean, we get string Boolean number. And if we instantiate with number, then we get string number. And if we instantiate with empty, we get string comma number. So in a sense, this is like tuple concatenation or construction of new tuples from other tuple types, right? one of the places where this is useful is that it's now possible to write strongly typed functions like, well, let me expand this guy here, like a concat function, for example, that concatenates two arrays. But if you model these arrays as tuples, or as possibly being tuples, then if at compile time the types of the two arguments are tuples, then we can actually now compute the final result. And so you'll see that spreading two tuples in an array literal will actually generate a tuple of type ... t, u. And so if we concat down here, you'll see that we end up at compile time knowing that, well, the result coming out of this concat call is going to be number, string, and if we then concat that into another tuple, we could get Boolean number, string, and so forth. Now, if one argument is a number array, for example, then you'll see that we get a tuple that starts with a Boolean and then ends with a number array. But of course, if this was more strongly typed, so where we now get 4 numbers, then we get a full-on strongly typed, and of course we could ask, well, and now we have the complete exact type. So a lot more precision in the type system here is possible with this feature. The corollary of constructing new tuples is using inference to take apart tuples. And so here's a last function, for example, where we declare the argument as being, well, so this function's purpose is to return the last element of an array. And if the array that gets passed in is known to be a tuple, well, then we can infer to a tuple consisting of something followed by a last element, u. And then we can simply return the type u. And say we pass in foo, 42, or true, you'll see that the last element gets inferred as Boolean. Here we get number, here we get string. And if we pass in an array, you'll see that we just get string or number. In fact, it's kind of interesting that the type system now is rich enough that you can express all of the traditional functional programming operators like head, tail, init, and last. If any of you have done any Haskell programming in the past, you'll know these operators, and now you can actually write them in our type system. So here you see you fetch the head of a tuple, that's the first element, the tail, those are the remaining elements. Init is all but the last element, and last is the last element. And that means that it's now possible to write functional style algorithms that operate on lists in the type system where the lists are represented as tuples, and we'll see other good uses of that. Inferring two tuple types, one scenario in particular we support here is the ability to split a tuple type in the middle. Here we're writing a bind function. If you think about how bind works, you pass it a function and some arguments, and then it returns a function that takes the remaining arguments. And we can model that by saying the arguments of the function that it takes is a tuple that is a combination of some first part and some second part. And the arguments that get passed are the first part. And then bind returns a function that takes the second part, and that function in turn will invoke and spread in both of the parts. And you'll note that inference can actually get this correct by inferring an implied arity from this argument here and understand where to slice the tuple, so to speak. So here, if we have a function that takes 4 arguments and we bind nothing, well, then we get back a function that also takes 4 arguments. But if we bind 1 argument, then we get one that takes 3 or 2 or 1 or none eventually. And it's all strongly typed. Now, one thing you'll notice here, by the way, is not only can we slice and dice in this bind function, but notice how the parameter names are actually preserved in the resulting functions here. And that's because we traffic parameter names through the inferred tuple and then spread them back in the result. And that feature has actually been around for a while, but it wasn't fully exposed. The only way you could get these names was by inferring them from one function, and then you could spread them into another function. So take an example here of let's say I have a callback function that takes some context and then some arguments. So I can use this to construct callback functions. And so if I want a callback that takes a single string, I could do it this way. And if I want one that takes two numbers, I can do it this way. But as you'll see, there are no argument names to be had here, and so we sort of have to make some up. And of course, that's not ideal. But if the parameter list passed to callback ultimately comes from something that was inferred from a function like here, for example, then you see that we can actually preserve it. And the reason we can preserve it, it used to not be visible, but now we're actually making it visible. So notice here that we infer a tuple where the elements are named, and you can actually yourself do that now. So if we look at the calls down here, you'll see here we have calls where we don't have argument names, but if we add argument names here like message or x comma y, oops, and then look again, you'll see that now we get parameter names in our functions. Now these names have no semantic meaning whatsoever. They purely exist for documentation purposes. You can't use them when you're accessing the elements. You always access tuple elements by indexing by 0, 1, 2, and so forth. But in cases where you spread a tuple into an argument list, they will be used as the parameter names. So that's labeled tuple elements, also a new feature. Spreads in array literals here. Let's look at this one. So when you spread tuples into array literals, we will actually infer, and you as asconst, then we will infer a variadic tuple type. So here you see the result of this function is a tuple consisting of 1, t, 2, etc., etc. And if you call it, we will accordingly infer a true static type. And finally, the corollary of that is, allowing you now, we have much better support for spreading tuples into parameter lists. So here we spread a tuple with 2 elements into a function call, and that counts as 2 arguments. And then the next one has 1 element that counts as 1 argument. And so we can satisfy the call in a variety of different ways, and we still get error checking in the normal way here. For example, T1 counted as 2 arguments here, but the function expected at least 3, and so we get an error. So that's variadic tuple types. Another interesting feature that, so we have class property inference from constructors. I'm not going to show that right now, but it's basically the ability to infer the type of properties declared in a class without a type annotation. We can infer their types from control flow analysis of the constructor. So we basically see what the constructor does and then infer the type accordingly. Catch clause type annotations is a long-standing request. We can take a quick look at that one here. Here's a catch, or here's a try catch. The way that you would write it in TypeScript, at least before 4.0. And this code has some issues because in JavaScript, it's really impossible to know what the type of an exception is going to be. And therefore, we say that an exception is always typed as any. And in the old days, any was our only top type, and that sort of made sense. But of course, any allows you to write anything you want here, and you can write things that absolutely don't make sense. And so this could actually be a cause of errors. We now permit you to put a type annotation. Of course, you can say any, but you can more importantly also say unknown, which is really the strict and more correct view of what's going on here. And now you're not permitted to do anything on E unless you first check appropriately. So here we would need to really actually ensure that E is an instance of error before we can access the message, or we would have to ensure that type of E triple equals string here if we want to do to uppercase, etc., etc. Now, the thing that's interesting is that you can't, for example, say E:string here, and we will complain and say the only thing you can write here is any or unknown, but now at least you can write it. We may later introduce a strict mode option that requires you to put an annotation or that turns the type into unknown always, but certainly it's very easy to construct a lint rule that verifies that you always have a type annotation here, and then that's another class of error that should be eliminated. So that is catch clauses. Lots of stuff happened in our tooling as well. Emit declaration files, etc. So I'll let you read over this. Maybe I will just call out a few of them. One is type checking speedups. In 3.9, we did a bunch of work to speed up type checking because we had seen a number of regressions in versions 3.5, 3.6, 7, and 8, and it turned out that we didn't really have good test coverage for some of the more advanced type system features used at scale. And so we sort of went on a hunt and found some of the really big sinners when it comes to heavily exercising the type system, in particular projects like Material UI and Style Components that we kept seeing regressions in. And we first of all found all the hotspots and did a series of pull requests to speed them up. And this is actually a guy at Microsoft in the Office group who saw massive gains in their compilation simply because we do better on those hotspots. But what we also did was we added then Material UI to our performance test suite so that we now have something that will measure or sound alarm bells if we ever start to regress again in that area. And sure enough, a couple of weeks ago, we had one pull request where we were trying to work on some functionality in discriminated unions. And all of a sudden the alarm bells went off, as you can see here, and then of course it turned out that we needed to do a little bit of extra work to not set them off. But I'm happy now that we have better coverage, and I think we should actually be able to not see regressions on this again, and also we managed to really make compilation faster. So I would highly, if you have not upgraded yet to 3.9 or later, I would certainly urge you to do that. Another feature that we introduced was the call hierarchy view. I don't know if any of you have actually seen that in action. We could show it here briefly. Say I have a bunch of functions. I could always, of course, use F12 and Shift F12 to navigate and find all references and so forth. But it's hard to sort of see an overall view of who calls who, and that's really what the call hierarchy view is about. So if I bring up the call hierarchy viewer, for frequently called function, you'll see that it shows that it's called by caller A and caller C, and you can click and see where. But then you can also see who calls caller A. Well, caller B does, and caller B in turn is called from entry point. But entry point also calls caller A and calls caller C. And so this gives you sort of a nice hierarchical view of the same information that we already have available in the compiler. It's just easier to navigate with this feature. Another interesting feature is partial semantic mode. Let me bring up some code while I talk about what that is. And I'll bring up a really large project, a VS Code project here. And I'm just going to helicopter right into the middle of some file in VS Code. Now, in order to do syntactic highlighting in the editor, VS Code will create a language service that only analyzes the current file, so that we can get an AST for the current file and then base syntactic highlighting and so forth on that. But in order to answer more semantic questions such as statement completion or whatever, we really need to know the entire program. So if you look at this code here, for example, we call promise.all, and then we call then, which means that domains is going to depend on what the all method does with its argument, and all comes from promise. And in order to figure out what promise means, well, we sort of have to figure out what are all the modules in the program and which one defines promise. And that means we need to parse and analyze all of the files in your project in order to be able to answer that. Of course, once everything settles down, I can say domains dot and get statement completion here. We know that it's an array of arrays. And likewise, we know for list here because it has a local type annotation. But previously, and let me try to close and then start up again. Previously, there would be a sometimes 15-second lag while we parse and build ASTs for all of the source files before we could answer any questions. But now we actually can sort of answer. So if we look at list dot, for example, you'll see here that we're able to give you statement completion right away. But if you hover over domains, you'll see that we don't know what its type is yet. It is still loading. And if I say domains dot, I don't get any statement completion yet. But after a while, you'll see that all of a sudden the type changes to string array because now we have completed in a separate process parsing all of the files, and now we actually know the full truth and can give you here now. There we go. Now I get the full statement completion. So what the way we do this is we use this syntactic language service to only analyze the current file and then just assume that everything that isn't declared in the current file has type any, and then we'll show you loading meanwhile, and then once everything completes, then we give you the full picture. So just a way that we make the tooling more responsive even on very large projects. Another new language feature is deprecated. Let's try to take a look at DAP. Here's a little example. Let's say I'm now going to introduce a new method called enlarge by some factor, colon number, arrow void. And then I want to deprecate the supersize function. So I can say at deprecated and say use enlarge instead. And you'll note that nice features light up, such as striking out deprecated and showing you what you should do instead. And if you say foo dot, you'll see that the enlarge method is here. But if I hover over supersize, you'll see, hey, no, go use enlarge instead. So I can do that. Nice little feature. This actually was implemented by a community member, so that's really great. So also lots of new refactorings and quick fixes. Lots happened in our website and documentation this year. A revised handbook, a new reference for TSConf, lots of translating, and then a new implementation of type search built also by community member Joshua Goldberg. Thank you very much. That makes it easier to find type declarations. So go check that out. And that's sort of what happened in the last year, but of course we're not done yet. TypeScript 4.1 is on its way out. And I'm going to give you a sneak peek of some of the features. Well, the beta is already out, and I'm sure some of you have played with it. But let me give you a little bit of a view of what's happening in TypeScript 4.1. Again, bunch of demos here. I'm going to jump right in on recursive conditional types. And let's just look at an example. That's probably the easiest way to understand this feature. Let's say I want to write a type that represents the type I get after awaiting a promise. Now you know that in TypeScript, promises can nest, which they can't actually in the real world, but in the type system, we can't really keep it from happening. So you can have something like a promise, a promise, a promise of string. But really, ultimately, when you await that, you're just going to get a string. And it would be nice to say, what is the awaited type of a promise? And this type reflects that. But by nature, it is a recursive guy, right? Because here we say if it's null or undefined, then just return T. Otherwise, if T is a promise, then infer its T and then await that. And keep doing that all the way down. This now works in TypeScript 4.1, and it all works as you would expect. But this feature was not available previously. If we go to TypeScript 4.0, for example, you'll see that we get circularity errors on this type here. But the funny thing is, it actually was possible to write the type using this strange device where you use index access types to index into an object literal with choices. But it was just very ugly. Yet people were writing types like this in the wild and actually writing recursive types. And that also meant that we in the compiler ended up doing a whole bunch of work to harden the compiler against infinite recursion and Stack Overflow. So we put in like recursion depth limiters for instantiation and for constraint reasoning and for type relationships and so forth. And all of that stuff has really sort of been put in place gradually. And we felt now it really was time to just lift the restriction on conditional types themselves and allow them to be written in a recursive manner. And so that's what we're doing with TypeScript 4.1. Now, what else can you do with this? Well, for example, you can write the type that is returned by array.flat. Which is a new method on array in ECMAScript that flattens an array. And that basically consists of first finding the element type of the innermost element type of the array, where we keep inferring until it is no longer an array, and then that's the type. And then the flattened type is an array of that innermost type. And so here, if I flatten a string array or I flatten one of these guys, we can drill in appropriately. But it's interesting to see what happens if I create an infinitely recurring array and then try to get the element type of that. And here you'll see our excessively deep error. This happens after we've gone 50 levels deep, and it seems to be going badly, or in that it's never stopping. And at that point, we trigger the recursion depth limiter in the compiler, and this is part of hardening the compiler, the work that we've done. And so we give you an error message here. So previously, things like that could cause the compiler to crash, but I think we've managed to chase down most of that now. Here's another example of for example, creating tuples of a certain length. That's a request that's been out there for a long time, and it's now possible to just do by writing types. Here we have a tuple of some element type t repeated n times. And we implement that by first distributing over n and then saying if n is a number, then just return an array. Otherwise, use this recursive worker here that creates a tuple of t comma n starting with an empty tuple. And then underbar tuple of says keep iterating until we reach the desired length. And what we do is if we have the desired length, then we're good. Otherwise, add another element to the tuple and recurse. This is actually a little functional programming language if you look at it. And indeed, with recursive conditional types and variadic tuples, we now have a lot of the elements of pure functional programming languages captured in the type system. And that means that you can write inference algorithms in this nice little pure functional programming language that is TypeScript's type system. And here you get a tuple of 3 elements, or because we distribute over unions, you get a tuple of 0, 2, or 4 elements, or just an array, or again, trigger the recursion depth limiter if you try to go too many times around. Another example, this was almost impossible to do previously, just a simple operation such as reversing the elements in a tuple. That can now be implemented beautifully as a little functional algorithm where we pattern match on if it's the empty tuple, then it's t. Otherwise, if it matches inferring to a head and a tail, then reverse the tail and put the head at the end, and then otherwise just do nothing. And here now we have the reverse tuple, which is all lovely. Let me close this one out. That is recursive or conditional types. Template literal types. This is where things start to get really interesting. Let me first actually set the stage a little bit. There's this issue that has been out there for 4 years now, where someone asked, can we please get the ability to modify the property names generated by map types? Up until now, map types have always just simply mapped the property names directly, and the only thing you could change was the type of the properties. But there are a lot of patterns in JavaScript where you create like async versions of methods, or event change blah 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 changed events methods that correspond to all of the named properties in an object and so forth. And lots of libraries do that. And it hasn't been possible to model that in the type system yet. There's obviously been a lot of demand for it. As you can see, this is yet again one of these heavily upvoted issues. So we decided to go to work on this. So that was sort of the motivator, if you will. And let me show you what it looks like in action. So the key workhorse really is this thing called template literal types. And template literal types are really quite simple. It's the ability to create new string literal types from existing string literal types. So for example, here is a type that takes some string type parameter and spreads it in to a template literal here and basically adds changed to it. These template literals here are just the same as JavaScript template literals, but the holes, where the holes are expressions in JavaScript, they are types in the type syntax. So here you don't put an expression, you put a type that is constrained to string or number or Boolean or big int. Now, then through instantiation, we can create new string literals. So here we pass in foo and we get the string literal foo changed. And if we pass in a union, it distributes and we get foo change, bar change, baz change. So you can see if this was key of some object now, we would have all of the changed property names just generated for us. In a sense, it's like a little pattern language here because we can express things like a a string literal that starts with top or bottom, followed by a dash, followed by left or right. And we will produce the cross product type here. So this becomes a union top left, top right, bottom left, bottom right. You can use it also to, in the type system, get the numeric or the string representation of a numeric type or a Boolean or of a big int. So here you see how those all become strings when you spread them in. And indeed, the holes can actually, in these examples you see here, we're dealing with finite types, unions of some finite set of elements. But ultimately, we have some types in TypeScript, some primitive types that are infinite, like string and number and big int have an infinite number of possible values, or at least for all practical purposes, infinite. But we still do allow you to express that as a pattern here, if you will. So this is something that consists of some string followed by dash followed by another string, or string dash number. And here I can assign a hello dash world, but if I don't have a dash, then I'm told that that's not assignable. And likewise down here, if this is not a number, then I get an error. Of course, you can make some very big union types this way. Here's a digit, and then here's 4 digits, which ends up having 10,000 members. And ultimately, these unions can get too large. If I add one more, you will see that we at this point go, no, this is too big. We can't represent it. And of course, you could speculate about us possibly deferring the resolution of types here until it's necessary and so forth. So that may be something that we will experiment with over time, but at least know now that there are some limits to what can be done here. Just like just like tuple types have variadic tuple types, and you can infer to variadic tuple types, so can you infer to string templates, and that becomes that becomes the way that you can decompose string literal types into constituent parts. For example, here's a type that decomposes some string literal that starts with open bracket followed by something, followed by comma, followed by something else, followed by a closed bracket, and then returns those 2 strings if it succeeds. And so here we get 1 and 2, or we get foo and bar. But here we don't match because there's a beginning blank, or here there's not a comma, or here we actually do succeed, even though there's because we have non-greedy matching. So we just match the first comma, and then the rest goes into the second. Of course, you combine this now with conditional types, and you can write little algorithmic types, such as a trim that gets rid of the blanks on both ends of a string literal, like so. And you can even go crazy and write types like join, similar to what exists in JavaScript, where we join up the elements of a tuple with a given separator. And here we get 1.2.3.4, or foo dash bar dash, etc., 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 or just a concatenation. And this is again done by writing recursive conditional types and using pattern matching in inference and whatever. It's a neat little functional programming language that exists here for expressing these things. The corollary of join is split. You can also write that one, and we can split strings into their constituent parts. And here you'll note that if there's no delimiter, then we have a convention that says when you're inferring to 2 holes in a row, then the first hole gets a single character and the second hole gets the rest. Now, so that's a bunch of workings here. Let's look at what it looks like in action then. We can go back to that motivating example that we had. Oh, and I see I'm a little bit over time, but I'm gonna finish up here. So we want, okay, we wanted to, the motivating example was sort of give me the ability to create all of these changed methods on an object. And so here's the combined version of that. We write a map type that iterates over the keys of T, but only the string keys of T. And then we turn each of those into blah changed. And then we turn the type into a callback function. And now we can make a thing that watches an object here with properties. And when we say Homer dot, you'll see that we have our properties, but then we also have our events, like age changed, for example. And in here, we can now get a new age arrow, and then say console log of the new age is so this is very real world. This exists in a number of frameworks, and this is one example of how template literal types come in handy. Another example is the ability to promisify APIs. If you have an API that uses callbacks, but you want to turn it into an API that uses promises, and maybe use a naming pattern where you call all of those blah 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 async. Here's how you do that in a few lines of functional type system code. And if we experiment here and see, we have our file system with .open, for example, that then requires us to supply a callback. But if we look at the type that comes out of the combined version, we now have FSA dot, and FSA has all of the same open, read, and close, but then it also has async versions of it. And open async, for example, you'll see takes a path that returns promise of number. And that was actually inferred from the callback in the type here, and then turned into a promise and so forth. But you'll also note, maybe one thing I'll note here is that we say we only promisify things where promisify succeeds. So the property name we use then is blah async, but if it doesn't succeed, then we use the property name never, and that causes the property to go away. So you can actually use this to also filter out properties, and you'll see that FSA here does not have a version async, because version is just a string and you can't really promisify that. Okay, final example is dotted paths, which is yet another. I'm not gonna go over exactly how these types work. We'll post all the examples so you can look at them elsewhere. But one pattern that is very common in state management libraries and OR mappers, and even Lodash has helper methods that work this way, is you want to have a function getProp or setProp where you pass an object and then you pass a dotted path to a property. That was not at all possible to express in TypeScript before, but it actually is now. So let's say we have a strongly typed object here with a name and an age, and then a cars property that's an array of, again, some objects with properties. And let's say that we just request statement completion on this property name. You'll see that we can now construct all of the possible property names. And if we select one of them, then we can also take them apart again and figure out what is the exact type of that. So cars.0.make is Trabant, but if we pick cars.1 is Trabant and 0 is Ford and so forth. So all of a sudden, you can get strong typing for these stringly typed APIs that previously were impossible to type. So that, I think, is pretty darn cool. Let me close this. And almost there. Let me jump back to the presentation here. Template literal types, key mapping, we looked at. Intrinsic string types, let's just take a quick look at that. These are funny types. It turns out that when you do this property remapping, it's often necessary to uppercase or lowercase or camel case or snake case or whatever your favorite casing convention is, change the identifiers around in some way. And ultimately, you need some utility helpers for that. It is technically possible to write an uppercase function in the type system itself, and a lowercase and capitalized and uncapitalized, but it would not be very efficient, and you'd have to replicate all of the Unicode code classification tables and whatever, which is kind of crazy. So instead, we have introduced sort of this notion of intrinsic types that can be implemented by the compiler, but otherwise look just like regular types. And so the compiler then implements these intrinsics that are now available. So you can uppercase on something of string literals, and you get the uppercase version of it. And here you see, for example, how you would write the on blah, blah, blah changed, where you want to capitalize the property. And let's say you have event name of foo, and you get like on foo changed, where foo is capitalized. And then again, you can use our nice little functional programming language to write your favorite casing using these primitives, so snake to camel case or snake to Pascal case, and you see how you can actually now map identifiers between all of these different forms, which again is super useful because there are lots of libraries that do that and have these conventions that you want to give strong types to. Okay, final new feature in 4.1, and this is all coming soon here in November, is the no unchecked index access compiler option. You're all familiar, I'm sure, with the strict option, which is really sort of an amalgam, a master switch for a whole bunch of other additional checks that can be turned on all at once. And this is actually the mode that we recommend that you compile in. But there are still checks that we could do that probably are even more strict than strict. We sometimes call them pedantic switches, and we toyed with having a pedantic mode. And one example is accessing arrays. If you look at simple code like this, I create an array, I initialize it somehow, and then I access one of its elements. Should this really be permitted? Well, technically, we are unable to prove that a sub I will produce a string, because the initialization of the string array, first of all, might not have put enough elements in, so we would need to somehow have verified that I is less than the length of the array. That can be hard to do, and even if we have verified that, the array might have been a sparse array, which is one of these funny features that JavaScript has, where arrays can have holes in them. So there might still not be a string in the array of that element. And it turns out that it is effectively impossible to verify that elements truly do exist. But some people still want us to complain and still want an error here. And with the no unchecked index access compiler option, we're giving you that capability. And basically, you are now required to, whenever you access an array element, other than one at a static index where the control flow analyzer can understand what's going on, you are required to prove that it's not undefined or guard against it with some default value. Now you might ask, why couldn't I just declare my array a string or undefined array, and then I could get the same effect as this compiler switch? Well, not really, because when you store elements into the array, you don't want to permit storing undefined. So with this feature, you must always store strings into the array, but you get string or undefined when you read out of the array. That is what's happening in TypeScript 4.1, and that takes me a little bit late here, I'm sorry, but takes me to the end of my talk. I want to say, again, thanks to all of you for using TypeScript. I want to encourage you to keep the contributions coming and to keep the suggestions coming on the issue tracker, and please vote on these suggestions, because that is very much what guides us in deciding what features to build next. And with that, I'm gonna yield the floor and let others get on with the conference here. So thank you all.